Hi guys and girls, welcome to this tutorial in which we will solve with the simulation technique the open model with a single Q station that in the previous tutorial was solved analytically. So we will use the JSIMgraph tool and we will answer the same question considered with JMVA. The simulation model considered is this one. It consists of three stations: a source station, a queue station, and a sink station. Service time is the amount of time required per visit here by the queue station, and the response time is the wait time plus the service time at the queue station. The arrival rate is the rate at which the requests are generated by the source, and the solution technique adopted is simulation with JSIMgraph tool. The parameters of the model were obtained from the data collected, we imagine from the data collected in a 2-hour period. So we have a measurement interval t, we have a number of requests executed in this measurement interval, and the ratio of c over t provides us the arrival rate lambda of 2 requests per second. We consider a workload that consists of a single class. So this assumption means that the requests executed by the system have similar characteristics, and thus their service demands can be described with their mean value and distribution. So we compute the mean value of all the service time required, that is 100 milliseconds, so 0.1 second. The distributions that we are going to use will be exponential, just to be consistent with the previous case used with JMVA, and the performance indices are the same considered before. So we have now to answer the questions that has already been considered. Now let's consider the first one.
I have a question. How can I compute the performance indices of the server with the actual workload?
Okay, now we should start to implement the simulation model. So here we have the first window of JMT, and we select in this case the JSIMgraph. Let me resize the window, one moment. Okay, so this window will appear once you click on JSIM. We start with new model. New model, we have said, that consists of a source, a queue station, and a sink station. Let's connect all these three stations, and let's align well with this feature. Okay, just for visual property, satisfy the visual property. Okay, now first we have to define the class that we are going to use. So we add the class, and the class we know is open, and the arrival rate was 2 requests per second, so the default is 1, the lambda. Now we have to select to edit. Exponential is default distribution, and we have lambda now that is 2, should be 2, okay, request per second, and JMT allows you to define the parameter that you want. Here we select the lambda, so the mean will be 0.5, or he will compute this one. Indeed, exponential is 1 over is the inverse of the lambda, or the mean, or the lambda is the inverse of the mean value. Don't forget that we have all the possible offered distribution, so we have several, but we select the exponential in order to be consistent with the previous example. So the arrival rate is defined. Now we should define here in the queue station the service section. Again, the service time is assumed to have exponential distribution, and we know, for example, that the mean was 0.1, so was 100 milliseconds, so we should define 0.1, so that's okay. Indeed the lambda is 10, and the routing is useless because we have only one path in output from the queue, so it's automatically selected also if it's random. And now we should select the performance indices. Let's select the indices that we are able also to that we used in the other example. So we select the remember the utilization of the server, the system response time, and the number of customers. Good. Let's consider now these new parameters that we have here with respect to the other. First, we have to select the station we are considering for this cell, for these indexes, and these two variables are essentially related to the accuracy of the estimated mean of the index measured, in this case the utilization or the system response time of the number of customers. So, for example, the 0.99 confidence level that we have here by default means used in this model to construct the confidence interval means that it contains the confidence interval computed contains the true unknown value of the mean with 99% of probability approximately. So by default, the collection of samples is stopped when the required precision is reached. Typically, the higher the confidence level used to construct the confidence interval, or the smaller the maximum relative error, the longer the simulation, since more precision is required and thus more samples must be collected. We will analyze this topic and the different options available for controlling the simulation experiments in a following tutorial devoted to this subject. Now let's consider also here the statistical results. This option means, for example, that we collect all the values of the system response time generated by during a simulation run, and several statistical indexes will be considered by them, by the tool, and will be shown to the user. We have now selected this selection, and also now we may start the simulation. Okay, that started. Let me resize the window again in order to see here. Well, the equilibrium, as you see from this green mark, is reached. Equilibrium means that we reached the precision required by those two variables, confidence interval and maximum relative error. And here you may see the mean value of the confidence intervals. As you may see, the more we collect sample, the more precision the confidence interval became short, and then until the one with the precision required is reached. So number of customer, utilization, oh, this is very small. Okay, we should go here, and system response time are here. So if you remember, we have a number of customers 0.25, and here the mean value is 0.249. 25 is in 0.25 is inside the confidence interval, so it's okay. Utilization 0.2 is perfect, as also the right value, and system response time is 0.125. This is a simple model. Now let's remark, for example, system response time. We have required the statistical results. So if we click here, and let me again, okay, resize the window, you will see all the statistical value computed on the value on the system response time, on the sample of system response time computed by the simulation. For example, here you see that the standard deviation is 0.1247, so the coefficient of variation is 1. This means that the value generated by the simulator are exponentially distributed, and the coefficient of variation is 1. So this is correct, because we know that the system response time analytically are exponentially distributed. Here, just to show you the graph, you have several options. You can filter the data, and also you may have graphs. For example, if you want to have histograms, here you have 10 number of interval. You may select 100 number of interval and redraw, and you have all the 100 histograms of the response time. Or if you want to have the percentile, simply distribution and you select 100 number of intervals. So here you have the distribution, and you may have, if you save this value through this button, you may have all the percentile values here. Okay, now let's go on. May select. Okay, I keep this because those are useful for the next answer. So here you have the analytical value correct that we have seen, that they are practically the ones that we required. Now
I have a question. How can I study the behavior of the performance indices with arrival rates ranging from 0 to 9.9 requests per second?
Well, in this case, what I want to show you is that we will use the what if of the tool, of the JMT tool. So from here, then from the JSIM tool, we may obtain this. This is the model we constructed before. So if you click on what if and we enable the what if, okay, we want to change the arrival rate. So here we select as a control parameter the arrival rates, and the range of the interval should be defined properly. We have to define, let me close this window and we open layer. Okay, the initial value of the lambda, instead of 2 that we set before, we have to set now 0.1, and okay, this is done. And the what if, now we have to select the other extreme of the range, that is, instead of 9.9, let me limit to 9.5, because as you will see, the simulation takes time. Now we ask 20, and one more, we must care about the precision. Here, for simulation parameter, the maximum number of samples to be collected before to stop is automatically is 10 million. Now let me decrease to 1 million, and then we will stop the collection of data. And also, in order to speed up the simulations, the simulation of 20 models, let me also take out the number of customers. Let's collect only utilization and system response times. Okay, now let's start the simulation. This simulation means that we simulate 20 models, ranging with the lambda arrival rate ranging from 0.1 to 9.5. So here you will see the number of the simulation executed. Means that until now we simulated 14 models out of 20, now 15. As you may see, the more the lambda increases, the more the value fluctuates, and so the more time is required, because the simulation became longer and longer due to the fact that the precision is more hard, takes more time, the required precision takes more time to be reached. So for that reason, when we are at the extreme values, like now 19 simulation, so it's close to 9.5, and the 20 is 9.5, takes more time, of course, in order to attain the precision. Okay, now all the values are obtained. Resizing the window, you will see here the utilization. Let's go to system response time, for example. Here you have the curve of system response time with all the values that we used. Here you will see also for each model solved the confidence intervals. What I want to point out, due to the fact that there are this arrow, red arrow, let me show you here, is that for several value of the gamma of the lambda arrival rate, the precision was not reached, and the control simulator stopped at 1 million requests, 1 million sample. Here you may see the confidence interval 1.977 means the mean response time, system response time, for 9.5. Okay, and so also here you see the confidence interval very short, very small. Now, okay, let's consider just to be consistent with the other.
I have a question. Which will be the maximum arrival rate in order to have a mean response time of 2 seconds?
This question, computing the R of 2 seconds, so we know that R of 2 seconds analytically, here you have the formula to derive is 9.5. So let me consider the results we obtained. Here is 9.5. As you may see in simulation, we have 1.977, and the precision required from the 0.99 and 0.03 of max error was not reached. So that means that if you want to have more precise values, you must increase the number of samples considered. Okay, well, this this tutorial, well, we have completed the tutorial, and we hope you enjoy JMT, and best regards.